So today, it's my big pleasure today to introduce you all to Gerd Zellweger, who is a systems researcher specializing in databases, database engines, and larger systems in general. He's been doing a lot of research work at VMware previously and at his current startup company that he's doing, and he'll talk to us about building database storage systems using Rust. So Gerd, take it away from here. I'm very happy to see you. And yes, the slides are visible. Oh, there we go.
All right. Hi, everybody. Thanks for the introduction. So this talk is called a storage architecture for the Feldera Incremental Compute Engine. And in the talk, I'm going to work backwards from the title. So I'll first talk about what is an incremental compute engine. Then I quickly show you how we use it in our product, Feldera. And finally, I'm going to talk a little bit in the second half of the talk about the storage architecture we built for it. And also, some learnings we had along the way of, how not to build a storage architecture. And hopefully this will be interesting. So let's get started. So what's incremental computation? That's generally not usually a well-known concept, but I'll explain it first. So let's consider the normal kind of computation we do. Usually what happens is we have a program P, we send that program some input, and the program produces the output, right? So that's not an incremental computation. But if we wanted to make it incremental, what it would look like is we would have a program that could, once we computed the first output from the input I, we would want to reuse that output. And if we change the input slightly, adding a delta I here, what the program would do is it would compute the changes to the output for us, right? So that's in essence incremental computation. And this can be much more efficient rather than computing the full output every time again. Now, in general, it's hard to kind of define this precisely, right? Because now we see we need this kind of plus operator. So we need to be able to apply a change to an existing, data set. And we also need to know what is a change, how we describe a change in the first place, right? So this isn't something we can do with every computation, but in practice, it turns out this works great for databases, right? So databases have a natural notion of changes. So P, our program here, is a query. The I is a set of tables we have. And the delta I is a transaction, meaning a change we send to this set of tables, right? And it also usually holds that the delta I, the change we want to send, is much smaller than the set of all the data we have in the tables. And the output, or the delta of the output that results from sending this change is much smaller than the total output we have in the database. And so there is a term for this in databases. They call this incremental view maintenance. So let me explain a little bit more from a database perspective how this looks like. So the normal non-incremental computation that databases do is, let's say we have a database here over time, and we have a time axis here on the x-axis, and we run this query against the database every time, right? And let's imagine the database has 1 billion rows. So every time we run a query, we have to go and compute the output by looking at these 1 billion rows, right? Now, if we change 100 rows, this would be the change that we do to the database. Few minutes later, we want to run the query again. We have to go look at the 1 billion rows to compute the output, right? So this can be very expensive if the query is, a very expensive queries and we have a lot of data. Now, instead, in incremental computation, what we do is we transform the query, or the original query here, such that the query only has to do compute proportional to the changes to be sending. So if we run the query for the first time in our 1 billion row data set, and we compute an output, and we send 100 changes to the database, the next time we only need to do this query that computes on the deltas to get the output. So in essence, that's incremental computation. And you can see that this can save you either a lot of time or a lot of compute resources. But it's a different way of how you traditionally would do computation in a database. Okay, so I hope this made some sense. So what we did actually is we built a general framework to allow building these kind of incremental queries and incremental query plans for arbitrary computation, right? And so we have an open source crates for this. It's called DBSP. You can look it up on crates.io. It has an open source license. And what it does is it has a lot of operators in there. Some are incremental, some are non-incremental. It's essentially a runtime system. You can compute on data in multi-core, and it supports, the relational algebra, meaning SQL. You can do nesting, you can do aggregates, and all kinds of stuff. I'll show you an example in a little bit of how this looks like. So what we do is we use this to, formulate all the incremental computation that we do in our product. And so here's the shape of how this would look like in a regular DBSP program looks like. So this is some Rust code. You see we have a main function here. And typically what you do is we call this a circuit because, our theory of how to do this has some influence from electrical engineering. So we build these kind of circuits. And, the circuit just takes a closure here. And then we see we define an input stream into the in that closure here. And that input takes just records. And then the first thing we do in this closure is we just inspect the records that we send to it by printing them out, right? And that would be kind of the basic shape of a circuit. Now, once you build that kind of circuit, what you would do is you would send some data into it. It would do the computation that you describe inside of build circuit. Then you can execute the computation, and then you can also send some output out of the circuit afterwards and read from it and see it. So that would be the resulting changes to the output. So here's a slightly more complicated way of building a circuit. So we see nothing much has changed except we added an output also to that circuit. And then instead of just inspecting the elements that we're sending into it, we're applying a filter to it where we look at the location field, and we would only allow output that either matches one of these kind of like location fields here. And so that would mean you can send a lot of records, and what you're getting out is like a filtered version of the collection. So that's a pretty basic kind of shape of a DBSP program. It doesn't really do much. It doesn't keep a lot of state, but what's kind of cool is that DBSP is powerful enough to represent all of SQL, right? To make all of SQL incremental. And so also in our product, right, in Feldera itself, the users typically, they don't write Rust programs, they write SQL code. So let me show you kind of like a quick demo of this, how it looks like in practice. So I'll switch to the kind of web console here of our product. And so what happens is I'm going to show you like a SQL program where essentially the way it works is that we have tables. Tables are just inputs for us where we send data to. And we have 3 tables here. This is kind of like a warehouse demo. We have warehouses itself. We have products that we can put into warehouses. And then we have a storage table that just says how much of which product we have in which warehouse. And then we kind of define outputs. So the outputs that we write are written as views, where views are just SQL queries that compute on the tables, right? So here I show you we have different views. This is an interesting one because it just computes the top 3 warehouses that have the most mass. But you can see, you can do joins, you can do group bys, you can do limits, sorting, etc. Average, max, min. And so what happens is we take this program, and there's a compiler that transforms this into one of those Rust circuits that I showed you just a minute ago. Right? And so once you have this Rust program, you can go and start it, right? And this is just a Rust binary in the end that runs in the background. And now we see we run this demo here, and we have the tables that I just showed you, and we can go inspect the tables too. And we're continuously sending data to it. So we have a bunch of warehouses that we inserted now in the warehouse table. We have products that we inserted. They have a mass and they have a volume. And we also have a storage table that stores which product is in which warehouse. And you see this table is slowly changing as we send data to it. Right? And so I also can show you that top 3 warehouse mass view, which changes more quickly depending on how much mass each warehouse has at the moment. And so the key part is, right, like as we send those changes to the pipeline, right, we only have to do compute proportional to the change that we send and not to all the data we've seen so far. And that's the beauty of incremental computation. That's why you can evaluate these queries very quickly and very efficiently. All right, so that's the gist of what we do. So now I'm going to go into kind of like the second part of the talk, where I talk about, what's the problem with that incremental computation, right? And so one kind of issue with this that, it's kind of like a trade-off, right? So by doing this computation, all this computation incrementally, you need to maintain a lot of state, so you don't have to always compute on the whole data set. And so if you build kind of like arbitrary, SQL programs, you can quickly, use a lot of DRAM, for example, when you send it data. And so one thing we can do about it to combat this is, we can garbage collect state that's no longer relevant. We can scale out, run these kind of like pipelines that I showed you on many machines. And we can also use persistence, right? So we can spill state that we maintain to disk as opposed to keeping everything in DRAM. And maybe, just to kind of like explain a little bit better. So in this query here, right, that I showed you before, where you just have a filter, you wouldn't have to maintain any state, right? You just apply this Boolean formula. But as soon as you start, doing aggregates, doing group bys, or joining like 2 tables, then you need to maintain state to do those join operations or those aggregate or distinct operations, right? So for that, you need to kind of like build these indexes as you would build indexes in a traditional database. Okay, so let me explain a little bit how we do maintain this state in DBSP. And so the key here is we use something called a CSET, right? And so I talked in the very beginning about how when we have state in when we want to do incremental computation in databases, we need to be able to represent changes to a database. And CSETs are really just that. They represent the change that you're doing to a database. This thing, each CSET has an integer weight. And the weight can be positive, 0, or negative. And we have different operations over CSET. We can iterate over the rows. We can look up something in a CSET by a key, or we can merge them. So let me explain this a little bit better. Down here is a CSET, right? And the CSET, it has a sorted list of tuples, which are the rows in the database. So here we have name and age. And so we have 4 rows in this CSET, and each CSET has a weight column added to it, and this can be an integer, right? So how do I read this? So this means in this transaction or in this kind of like change set here, I have a row of Alice with an age of 10, and because the weight is 1, that means I just have it's 1 row, right? It has a magnitude of 1. So I have also Beat and 12 with a weight of 3. So that just means I have 3 rows now of this particular tuple in my CSET. And Bob 8 with a -1 means I actually have a negative weight here. So that means I'm deleting 1 row of Bob 8 with this change. And then I have Chris 10 too. That means I'm also kind of inserting a row of Chris 10 twice. Right, so that's the meaning of the weight in this sense. And so what's nice about C-sets is they're essentially in mathematics or in type theory, you would say it's a commutative group, meaning you can merge two C-sets, you can take two changes and you can merge them together. There is a plus operator, right, to it. And so the way you do that is basically you try to sum up the weights, right? So in here, we're merging this C-set with this C-set. So we're taking AME1 and we add it, and it's not in the other C-set. So it just gets outputted as AME1 in the new C-set. Chris is interesting because it appears in both C-sets. So if I sum those weights, +3, -3 is 0, so it cancels each other's out. So I can delete it in the resulting new C-set. Mike -1 is also only just in one C-set, so I can just move it over. And John 2, John 1 appears in both. So again, I sum up the weights and I add a John 3 in the new C-set. So that's the merging operation, right? Okay, and so when we, what other thing we do is we store C-set inside an LSM tree. So, as the index is built up of changes, right? So what you can think of how we do that is we just keep a list of changes, right, in the most basic abstract sense in an index in DBSP. So, as changes come in, we aggregate them and keep a list of it. And then one nice thing you can do with that is you can basically still build the original operations I just showed you. So if you wanted to kind of like find a certain row in that LSM tree, what you would do is you would just iterate over all the C-sets simultaneously, and you find Dan 1, -1 in the first one, you find Dan 3 in the second one, and you don't find the Dan in the third one. So what you yield in your kind of like iterator implementation would just be Dan 2 by summing up those weights here, or -1 + 3. And you can have a generic iterator, so you can go to the next row, right, to find it would yield add and sum up these weights. And you can just iterate the whole tree by doing that. And so keeping these collections of changes, usually what happens is, right, like as the system runs, as you get like more and more transactions sent to it that end up as C-sets inside this tree, it can become a very large amount of changes that you have amassed inside your tree. And so you want to kind of like balance the amount of reads you need to do in order to find certain keys in it, because you would have to go look in every C-set whether the change is in there. But you can kind of use the merging operations I explained you before to keep that in check, right? To reduce the amount of C-sets you have. So every time you have too many of them, you just take two, like you take this one here and this one here, and you merge them into a new one. So you reduce the amount you have. So that's essentially how our indexes are built inside of this DBSP program whenever we need to remember state. And so there's also threads, right, that periodically compact them, similar to what I just showed you. And so if we wanted to like have a storage engine, right, for DBSP, all it would entail is just taking those, C-set or sorted vectors of changes and write them to disk, right? And ideally you would just take the large ones and keep the smaller ones in memory, etc., etc. That's basically what the LSM tree does for you. And if you're kind of like familiar with the key value stores, this is essentially how key value stores, or modern key value stores at least, work, right? And so when we started, trying to build a storage engine for this Feldera project, we said, well, why don't we just use an existing key value store? Because it has essentially this architecture I just explained you here. And so this brings me to kind of like the second part of the talk, where I'm going to talk about how we built this storage engine. And first, we started out using RocksDB. RocksDB is a production-ready key value store. It's open source, maintained by Meta. And, like I said, it matched nicely with our in-memory design, because in memory, we use this LSM tree to manage the C-sets, and the RocksDB is essentially an implementation of this same LSM tree. And so we built it. It was actually very nice, a very simple integration because, it has a very rich Rust crate already available. And, it didn't need a lot of code to build an index using RocksDB for us. Now, the sad part was that once we run some benchmarks with it, we realized that performance was really slow, or it wasn't performing very well. And so here's a kind of like a graph that shows the throughput for Nextmark queries. I only show the queries here that have state. So I'm skipping some, but you see, like, compared to the DRAM version of Feldera, RocksDB performed much less, had much less throughput. I'm also note here that the graph has a y-axis, log axis, so it's much less, so it's much severe than it would look on a linear axis. So what happened is there's a few reasons for why this is slow. I'm going into them in the next few slides. But essentially, the first thing we noticed is that we saw that we had very low scalability. So as soon as we started to use more threads, right, RocksDB would slow down with increasing amount of threads that we used for the pipeline. So DBSP itself is multi-threaded. It can make use of several threads. And RocksDB is multi-threaded too, but as you throw more threads at it, as you use it from more threads, it actually gets slower, right? So this is typically an issue that is very common in kind of like multi-threaded applications, that they don't necessarily scale that well. And the reason kind of for that is just, I would say it's mostly a design kind of like reason, where RocksDB is designed for a general use case where all threads can access all data. So in the kind of like the green bar, you show afterwards we show the storage engine that we designed for Feldera, and because our DBSP circuits, they use a shared knotting architecture where every thread computes on different data, and there is very little sharing, and if there is sharing, it's done explicitly through message passing. So that means there's no need to coordinate for the threads for accessing their own indexes, right? They each have partitioned indexes. And that allows you to kind of like write a version of storage that uses very little locking inside of it, and so has very little contention. So if you use more and more threads, it doesn't slow you down as much, right? So that's the gist of that. Another kind of issue we noticed with RocksDB was we paid a high cost of data deserialization, right? Because data is now loaded from disk, so you typically have a set of bytes that you're getting back from RocksDB, and then you need to take those bytes and make them into a concrete type, right? If you want to store them. Even worse, like in our system, we wanted to work for arbitrary Rust types, and the Rust types, they might have a custom ordering defined on them. So in order to sort, the keys, we would need to make these types from bytes every time we would do a seek operation in our index, right? So if you do a seek, you have to compare two keys. And here's a way to do that, which is how it looked like in our RocksDB prototype. So we just took the bytes and we transformed them into the original Rust type, and then we called the comparator function on it. And this is bad if, for example, your type is a string or has multiple strings inside in the key, then you need to do allocations right now in order to manifest that key, which makes things very slow. So you can see this here. So this is like a perf profile. It doesn't really mean much, but one thing you can see once we started profiling really the pipelines is, we saw a lot of like key comparator function. We saw this RocksDB comparator. So there was a lot of that showed up now as the most expensive functions, which before didn't show up at all, right, in the in-memory version. So what's kind of like funny about this is we can actually fix this, right? So in Rust, you have a lot of libraries or multiple libraries that do zero copy deserialization. So you could, which means you want to use the data representation that just takes those bytes that you're getting from RocksDB and essentially cast that directly, that address you're getting directly into a Rust type. And one thing here is a shout out to the archive library, which is great because it exactly solves this problem for us. So in archive, every serialized type T has an alternative representation, tarchive, and with the tarchive type that you're getting from just applying a macro to the original type, is that you can do zero copy deserialization, right? So you can just get a cast that kind of like bytes that you're getting that you slice to t.archive, and everything should work great. And even in addition, you also have a kind of like a powerful trait system that allows you to kind of compare between T archived and the original type T. The one thing that we didn't have was a file format that uses archive to store the C sets. So that's something we built in our storage engine in the end. And so if you think about it, right, like you could just use archive together with RocksDB. And so here we're seeing we slightly changed this key comparator function from RocksDB. So we now use this check archive root functions, which instead of like making a real type k, gives us just a type key.archived. And that is just a cast, right? It doesn't require any allocations. And so we could just compare these two archive types that are not expensive to deserialize. If you do that in RocksDB, you'll find that once you run your workload, at some point things start to crash, right? And the reason it crashes is because typically the alignment is not guaranteed when you do these kind of casts. So what happens is RocksDB returns a slice of bytes to you, right? This has an alignment requirement of 1 in Rust. And then when you want to make a kind of like a more proper type key archived here, that might have a different alignment requirement than what RocksDB provides you with this slice here. And so, typically you would start to panic here, right? And so because RocksDB is not built with kind of like any alignment requirements for Rust programs, unfortunately, this doesn't work, this kind of method of doing things. Yeah, so in our storage system, we were able to fix that, right, by making sure that whatever we load from disk, right, and however we lay it out in the disk in those blocks, and we load it from, and the buffers we hand you out always have the proper alignment for the original type that we want to deserialize into. Okay, so that was it for my talk. Thank you very much for listening. So if you want to try out, or if you want to use incremental computation in your use case, feel free to check out our GitHub repo. It's all open source. You can try it. We have a Docker image you can easily run, or you can use also a sandbox online. I also wrote a blog post on this earlier this week, and you can read it up if my talk or my explanations didn't make much sense. There's also a few more reasons of why we struggled with RocksDB with our storage engine, and why we ended up building our own storage engine. All right, so that's it for my talk. Thank you very much.
Thank you. This was very, very, very educational talk, because I've never, even though some compiler systems are using something similar. So for example, when you change code, your IDE has to react to those changes. And behind the scenes, things like Rust Analyzer, they maintain the internal state of your program, and then they have to patch this state. So it's very, very similar to what your system is doing. So the applications are far beyond just data storage in general, but it's very, very cool to see this idea of incremental changes getting into databases. My biggest joy to see, even though people like to badmouth SQL, I really like the fact that you just come up with the standard kind of let's say familiar interface to this, and the product demo that you did, it looked really, really nice. People are asking what would be the use cases for this kind of database as opposed to traditional persistent stuff? Because traditional stuff we kind of all understand. This looks cool, but hard to say how do I use it in the application?
Oh, that's a great question. So this is generally interesting if, for example, you have, let's say in your traditional database, let's say you have a traditional database workload. The place where this can be interesting is if you have a very expensive query that you want to run more often, right? Things that come to mind are operational use cases. Like let's say you want to power a dashboard. In order to compute the data you want to display in that dashboard, you need to run a batch query, right? And you know, let's say you want to have new results every minute or every second, right? But your batch query, because it has to look at all the data, would run for hours, right? So that would be like an ideal use case. So like analytics is one thing. Other use cases would be things like, doing feature computation for ML on the fly, right? So that's something like people use this for, where, they want to, for example, they have credit card transactions that are coming in. They have a bunch of like resident state of like customer data that they already have in there. And now, they're sending new transactions, and they want to quickly compute features that they use to identify fraud, for example.
Yep.
So that's a use case where this is very helpful, because the relation can be very fast. And in order to compute those features, you might have to take your transactional data, join it with some customer data that you have in already dormant in your database, and then you have like new continuous data coming in, and you want to quickly produce output. So that's another place where it is useful. Other kind of use cases we see is like IoT, for example. IoT is interesting, because people have, like, let's say, a lot of devices out there, that compute data, and they continuously send that data to a manufacturer or a seller. And then what the manufacturer wants to do is he wants to not necessarily take all those data, right, and store it, but he wants to first, filter, aggregate, over certain time windows, and then do kind of like these kind of like computations, and then not store all the raw data, but at least reduce the amount of data a little bit before they end up storing it, right? And then this is also something that this can do very well. Computations over like bounded time windows and stuff like that, to kind of like average or get a maximum and things like that. So yeah, so I think those are kind of like main use cases. But like you said, right, like I think this way of doing computation, it has many applications in many different domains. For example, compilers is one of them, where this would be where this is interesting too, actually, right? So it's not exactly what we do, but the kind of the theoretical background for it would be applicable as well.
Yeah, people mentioned polars and data frames, other analytical tools. They're asking like, what's the difference between those and the database doing this work instead of like an external tool doing this?
Yeah, so what was the first one? I understood data frames, and what was the first term?
Polars, I think it's
so actually when I posted this blog post, it was on Reddit earlier this week, and somebody suggested polars as a way of also interfacing with being able to like integrate this with polars. And so there's two kind of like answers to this question. So first of all, we have a Python SDK, which allows you to send data from Python to this query engine that I showed you here, and then get data back from the query engine. And the kind of like the API surface for that is pandas data frames. So you're right. So you take pandas data frames and then send data from that, and also get data back as a pandas data frame. So that's possible. But I think the question is more about directly integrating with something like polars. So you could take a query plan from polars and convert that into a DBSP program and then run that. So that would be something that's possible. We don't have support for that, but if this is really a feature you would like to see, feel free to go to our GitHub link, right? Oops, sorry, I messed it up. Feel free to go to our GitHub link and make an issue about it, and we'll happily consider it, right? If like many people request this feature as something to do, because yeah, it's a good question of what's the right interface, right? So right now we think SQL is a good interface, but if it turns out people really want polars, then it's just a change in the compiler, right, to make it generate a polar something that works together with polars.
So more kind of like storage computing question. So what would be more challenging for this kind of incremental computing environment. When you have like a few tuples that are being, or few records that are being changed over and over while others are kind of dormant, or it would be more difficult to work with data set where a lot of changes are spread out across different roles and stuff.
Right. So that's a very good question, actually. I'm not sure if I have a good answer right now. So, you know, one thing, the way it works in the LSM tree is, you know, as a change comes in, you just, for now, right, you put it in your collection of changes that you have. And then over time, you go and you merge those changes again to make them smaller. So the trade-off is really as if you have a huge amount of changes coming in, your reads slow down, right? Because as I showed you in that original tree, let me see if I can go back to it, right? Yep. If that tree here grows too big, it has too many changes, then when you seek something, right, you have to look up that you have to try to find that key in every change set that you're having inside your LSM tree, right? So as you insert more and more and more of these C sets, reads get slower, and then you need to compact them in order to make the reads faster again, right? To reduce the amount of C sets, tree here, to find an entry. So that's one thing that you want to balance. And then the other thing you want to balance is, you know, if you have very, very large sets, right, and very small sets, you want to merge sets of the same size together, right? Because you know, it doesn't make sense to like write a new 1 terabyte set by merging, you know, a set of like a few kilobytes together, right? So because you know that is something you can do to control the writes. So there's a lot of kind of like these tricks you can play in order to, you know, help with performance inside of these trees. They're all pretty well known. You know, the key value stores have all kind of like studied this thing very extensively. But yeah, in terms of like whether you want to, what's better, if you want to change just a few elements every time, if that's worse than, you know, getting a lot of new elements, I don't think it matters that much. I think the things that matter much more for performance is, you know, how you manage your compaction of the tree, how you manage, you know, being able to, like what you pick, how do you compact things together, and how quickly you can, you know, reduce the amount of sets as they arrive. I think those are the key parts.
Somewhat like my question that is not from the list. But I thought when you started talking about like alignment of the data in RocksDB rows, right? Could it be possible to like alter RocksDB storage in such a way that it would write aligned data?
Yeah, I think it's possible. It's definitely possible. I haven't looked personally like too deep into the RocksDB code to see, you know, how involved the change would be. I can imagine two scenarios. One is like, you know, you change this one like static, you know, macro that you have somewhere in your C code, and, you know, things just magically work out. And I could imagine another scenario where, you know, it's a really involved change, right? So I could imagine both cases. I'm not sure which one it is for RocksDB. What I do think is like if you make such a change, it will likely, at least in my mind, without being like too familiar about the data format, right? It will likely break the existing data format that RocksDB has, right, to store the data on disk. So those might be things you would have to maybe version it or something. I'm sure they all do that.
Yeah. I could imagine a scenario where people already have data in RocksDB, and they would just assume that that Feldera can work on top of it, and it doesn't, right? Because it needs to rewrite the whole database in order to fix the alignment.
Yeah,
right.
So that would be one. That would be bad. Yeah. Yeah, so I think it could be either way. I don't know which one is the right answer, but it would be interesting if somebody, could make a patch and send it to RocksDB, like to have to be able to specify alignment for your types or for the data you're storing as an alternative, as a feature for RocksDB would be really neat, right? To be able to say, hey, as a config option, I want this alignment always for my data. And then, that's the alignment you're guaranteed to have. That's something that doesn't exist.
Yeah, or alternatively, somehow like convince archive. I have no idea how to pronounce this this library name, but to convince them to, like, if they do the ref into, I don't know, str or just set of or uslice, just kind of let the ref to have some, I don't know, garbage in front, let's say, if it's unaligned, but still when you present this data, like you print it or you copied it over, etc., in those cases you would realign the data when you copy it and write.
Right.
Yeah, so there are multiple ways to go around it, and probably writing your own storage engine is a good way to actually make sure that you will not break someone else's code in the process. So kudos to you for making all of this work. People asking, like, can this all run on several machines? And if yes, how does synchronization works across machines?
Yeah, so there is a way to run a pipeline in a distributed fashion, right? So be able to like run it into on different machines. So the way it works is like it's a Dockerized environment then. So it will run different like Docker containers that communicate with each other. And the way we do it is it just uses message passing. So it uses just normal networking to communicate with each other. The way it looks like on the circuit level is there are certain operators, right, that we use to exchange data. Like there's, shuffle operators and stuff like that communicate with all the workers in the circuit and exchange data with each other. So that's the distributed version. And yeah, so we have a support for that. What's nice, right, is that actually in many cases that we find, that actually, a single machine is great, is good enough for this, right? Because really it changes the amount of compute you're doing, right? Like on a theoretical level, right? So rather than, as I showed in the beginning, rather than when you have a query that you run against the database, the query doesn't run on that billion rows anymore, right? That you have in your database. It only runs on the amount of changes you're sending continuously database, which is computationally much less intensive, right? So that's a nice thing about this, is that you will need much less compute resources than you think or than you're used to from like traditional like query engines like Spark, right? Or things that are generally very compute intensive and consume a lot of resources. So that's the nice thing about this kind of
and in general, like, we are kind of, without realizing it, we shifted to this new era of cloud computing where we can get VMs with like 0.5 terabyte of memory. Right. So your database is like full in memory, but behind the scenes it can still be powered by a single machine, no problem. And in addition to that, you don't need as much compute to make it happen and to make it work, which is very, very cool.
Exactly.
All right. I think there was one follow-up question that I suspect was related to previous discussion about pandas and frames, etc. About like, if you integrate Feldera into your kind of Python analytics pipeline, it would introduce network latency, and this could potentially slow things down and reduce the benefits that you get from running this fast incremental computation engine. But I think you can technically run everything on a single machine.
Right? Yeah, that's correct. So you could run, your Python on the same machine as your engine, as your pipeline runs. So that's possible. Also, I think, it depends, right? Like if you have like a very small kind of use case where, it doesn't really matter that much whether you use Python or whether you use something like Rust underneath to do the data processing, then yeah, I think you might be fine with just using Python and data frames to do the computation. This comes into play when you have like a huge amount of data that you're sending, right? And then, doing all these computations for it. And I think, normally in these production use cases, you would kind of like separate the data processing anyways from, or that kind of like computation anyways would run it on a different, maybe Docker container too, just from an architectural point of view. So.
Yeah, I think these are all questions we had today. On a personal note, I used to work on in IoT space. And when you mentioned like all these devices sending data, it was like, and I was thinking, I wish I had this technology 5 years ago.
Right.
Yeah. I don't work in that company anymore, but I will definitely, I definitely think that a lot of IoT manufacturing companies would really, really appreciate a product like this. So I wish you best of luck with work on a company, and just with the project itself. Hopefully you like Rust enough to keep writing the system, and would like to hear from you again.
All right. Thank you, everybody.